What is going on, guys? Welcome back. In this video today we're going to learn how to easily work with cellular automata in Python using a package called cellpylib. So let us get right into it. Now, before we get into the actual tutorial, I would like to mention that this video is sponsored by Julius AI, a personal data science AI assistant. And the idea is that you can use it to do data science tasks without you yourself doing any coding, any data science, any machine learning work. Or you can also use this to let it do the work and then analyze it to learn if you want to do that. And this AI is specialized on doing things like visualizing data, analyzing data, going through the full machine learning pipeline, or writing reports, for example. I can show you here 3 example threads. One simple example where I upload a PDF invoice and it tells me what the content is. Another one where it actually can use the internet to query the Microsoft stock price and then it can display it in a simple chart. And also a more complex example where I upload a Kaggle dataset, a CSV file containing housing data, and then I just have to provide very basic instructions to get it to go through the full machine learning pipeline to extract for me the most important features for deciding the value of a house in a certain area. And in the end, I also get a nice visualization as a result here, highlighting the key factors influencing property prices. So this is an AI assistant that you can use with very little knowledge. And as I said, you can also look at the code it writes to see what it does so that you can learn for yourself. So if you're interested, check it out in the link in the description down below. Alright, so we're going to learn how to work with cellular automata in Python today. And we're going to do that using a third-party package called cellpylib, which is going to make everything easier and more structured for us. Now, for those of you who don't know what cellular automata are at all, I'm going to briefly explain the concept using my paint here, using a sketch. It's not going to be the most beautiful sketch you've ever seen, but it's going to explain the concept quite well. Now, let's start with a very simple CA, with a very simple cellular automaton. The basic idea of a cellular automaton is it's a grid of cells that have certain states in combination with certain state transition rules. So let's use a very simple example of just a one-dimensional CA. And this would be just a row of cells. So if we have n cells, it would be a 1 times n grid, something like this. And now each cell here has a certain state. In the most simple case, you have just 0 and 1, off and on. And then you can say, for example, we have the current state is 0, 0, 1, 0, 1, 1, 0. That is the current state of the cellular automaton. And then you have certain state transition rules. So for each cell, how do we decide what's going to be the state in the next iteration? So if I go forward 1 step in time, what happens to each individual position here? And you can define the rules however you like. You can say something like, okay, if both the neighbors you have are on, you become on as well. So this would be something like 1, 0, 1 translates to 1, 1, 1, or transforms into 1, 1, 1. And then you could say something like, if you have 2 inactive neighbors, then you become inactive yourself. Whatever, you can make arbitrary rules. But if you want to have interesting CAs, interesting cellular automata, then of course you want to use some interesting rules as well. And this is not limited to just 1 dimension. You can of course extend this to 2 dimensions. And one very well-known 2D CA is the game of life. So Conway's game of life, where you have very basic rules which result in quite interesting behavior. So in this case, of course, your neighbors would not just be left and right. Your neighbors would be, for example, something like the Moore neighborhood, where you just have the 8 cells around you. Now this takes some time to draw here. I'm trying to make it somewhat appealing here. But let's say, for example, I have this cell that I want to look at. The neighborhood of this cell, the Moore neighborhood of this cell, would be just the 8 cells surrounding it. But of course, you can define it differently if you want to. For example, you could also say that the neighborhood are just these cells here. So you don't consider the diagonals. This is also a possibility. But that is the basic idea behind cellular automata. And this is what we're going to learn how to work with in Python today. We're going to work with predefined rules. We're going to work with the Stephen Wolfram new kind of science rules, with the Conway's game of life rules, and we're going to implement our own rules just to see how it works. This is a very interesting topic in my opinion, so we're going to explore it a bit. Now, the first thing we're going to do is we're going to open up the command line and we're going to use pip to install cellpylib like this. And we're also going to install NumPy and matplotlib. Now NumPy we're going to use mainly for creating states and arrays, and matplotlib is going to be used for the visualization. Now once you have these three packages installed, we can start with the coding, and we're going to import cellpylib as CPL, and also NumPy as NP. So let's start with a very basic rule. Now you don't need to know who Stephen Wolfram is or what new kind of science is, but there is a system for defining rules in the NKS, new kind of science, which basically works like this. What you see here is the rule called 110. Now, why is this rule called 110? Don't be confused by that. It's not that complicated if you understand at least what the binary system is. So what you can see here at the top is you have the state. This is considering now one-dimensional CAs. So what we saw, just a row of cells. And imagine you have a long row of cells. This here are the transition rules for the individual states. And we're always looking at the center, at the middle cell here, how the state of the cell is going to change. In this case, when we read it from right to left, what we see here is that if our cell has two inactive neighbors and is itself inactive, it stays inactive. If our middle cell is inactive and the right neighbor is active, so the center cell is inactive, the right neighbor is active, and the left neighbor is inactive, this turns the cell in the middle to active. Then if we have an active cell with two inactive neighbors, it stays active. If we have an active cell where the right neighbor is active, the left neighbor is not, it also stays active, and so on and so forth. You can see here the basic idea. The center or the middle cell is always the one we're talking about, and then we look at left and right neighbor, and depending on the state, we transition to the new state, which is only for the middle piece. So if we have an inactive cell surrounded by two active cells, it turns into an active cell. Now, why is this rule called 110? Very simple to understand. Open up a calculator, set it to programming mode, and type in 110. What you will see is that this translates into binary 0, 1, 1, 0, 1, 1, 1, 0. And if you look at this here now, what do we have here? 0, 1, 1, 0, 1, 1, 1, 0. That is exactly what we have here. So the order is always the same. We go from 0, 0, 0 at the top here to 0, 0, 1, 0, 1, 0. So we go basically in binary from 1, 2, 3, 4, 5, 6, 7, 8. And then the number here, the state transition rules, are just the binary representation. You turn that into decimal. And then you can use that as a key code, as an identifier for the rule that you want to use in the new kind of science. I hope this was not too complicated, but the basic idea now is, let's say I want to keep the same rule set, but I want to change one thing. If all the cells are active, I also want to keep it active. So I want to change this here to result in active as well. All I would have to do for that is I would have to say that my rule is now 1, 1, 1. So not 0, 1, 1, but 1, 1, 1, then 0, then 1, 1, 1, and 0 again. And now I just have to turn this into decimal, which is 238, and that would be the rule 238. That's how the system works. I hope this was not too confusing now. So let's visualize, or let's use this rule here, this 110 NKS rule here, as the rule for our first cellular automaton that we're going to implement here. So I'm going to say cellular automaton is going to be equal to NP array. And I can start now with an arbitrary state. I can put everything to 0. I can set everything to 1. I can do something in between. What I'm going to do is I'm going to just pick 0, 0, 1, 0, 0 as a starting point. So this is going to be my CA. It's going to have just 5 cells. And one thing that's important is when you're considering the neighborhood of this cell here, the right neighbor is obviously this here, but the left neighbor is this here. So it goes full circle basically. Yeah, so that is our default state, and all we have to do now to evolve according to rule 110, according to this rule here, what we have to do is we have to say cellular automaton is equal to CPL evolve, and then we pass the cellular automaton. We say we want to do 5 time steps, so 5 steps of evolution or of computing, you could say. We can set memoize to true. And then the important thing now is applying the rule. The apply rule is going to be, in our case, a lambda function, an anonymous function that takes 3 parameters, and the most important one is the first one. It takes n, c, and t. We're not going to talk too much about c and t here. The important thing is n is the neighborhood. So we pass this to the following function, cpl nks rule, new kind of science rule. We pass n here, the neighborhood, and the rule is going to be 110, which is the rule that we saw here. So this is how it works. What this basically means is now that we take this default state and we apply this 110 rule 5 times. And all of the results and all of the intermediate steps are stored in this CA here. So what I can do easily now is I can say cpl plot cellular automaton. And I can run this, and then you can see what happens here. And you can open up the rules again to see that all of this is accurate. We start with 0, 0, 1, 0, 0. And what is the rule here for this cell? It says, okay, right neighbor is active, left neighbor is inactive, so the new cell is now active. You can see here we have active and both neighbors inactive. It remains active. So you can see that this is now the transition here. Here for this cell, we have left neighbor active, right neighbor inactive, so it stays inactive. And you can see that then we start with a new state and we apply the rules again, and so on. And of course, you can do that not just for 5 steps, you can do that for 20 steps if you want to. And in this case, it stays 0, 0, 0, because that is, I think, the transition that this ends up in. But I can maybe start with a different or with a larger CA. And then you can see that we get some more interesting results here. So that is very simple. We can also easily go ahead and change this to rule 30, which is also, I think, a very popular rule because it produces interesting patterns. And I think maybe it makes sense to add some more zeros here to get a more interesting result. But you can see what this basically looks like. All right, so that is how you can do that. The important thing is you have a CA, you have a grid, and you have a rule. This rule in this case is a predefined NKS rule that is well known, so you can just pass an NKS rule number and then you get it. But you can of course also pass your own custom function, which is what we're going to do later on. But for now, I want to show you first of all, just so you can play around with this a little bit, I want to show you how you can animate all of this. So how can you go ahead and animate this, not just showing the result in the end, but show the actual evolution steps. We can do that by using matplotlib. So I'm going to import up here, import matplotlib.pyplot as PLT, import matplotlib.animation as animation, and import, no, actually we already have cellpylib. So what we're going to do now is we're going to say we want to have a figure and an axis, which is going to be PLT subplots. Then I'm going to say mat equals ax mat show, and we're going to show the cellular automaton. The map is going to be binary, so black and white. And we're going to disable the axis here. And then what we're going to do is we're going to define a function animate, which takes I, the iteration basically. And we're going to set mat set data cellular automaton up until I plus 1. This means with increasing I, we're going to show more and more of the process of this CA. And then I can just return this matrix here. All right, and then I can say the animation is going to be equal to animation animation.function animation. I'm passing the figure, I'm passing the animate function. I say frames equals 30, interval equals 50. And for this, the frames, if they are 30, we should set this to 30 here as well. Interval is going to be 50. This is just going to be the speed. Split is going to be equal to true, and then repeat is going to be equal to false, so we don't end up in an endless loop. And in the end, I want to do PLT show to keep the final result. And what you see now is you can see the evolution of this CA. What's also interesting is we don't have to initialize it like this. We can also use functions from CPL. So from cellpylib, we can say cellular automaton is equal to cpl initialize simple. And I can say initialize simple 30 to basically get started with the same structure, with 0, 0, 0 up until the center, then a single 1, and then zeros again. But then you can see what this looks like. And I can also make this 100. And then you can see how this evolves. And of course, I can also add more time steps. I can say I want to have 50 time steps and 50 frames. And then you can see the animation here of this particular rule. And we can change this back to 110. This is going to result in something else. It goes to the left only, as you can see. But this is also an interesting pattern to look at. So that is the basic idea behind working with this package. Now we can extend this now to 2 dimensions. We can go ahead and, for example, implement the game of life. Now to do that, we need to have a different automaton dimension here. We need to have a 2-dimensional grid, but we can do that easily by just saying cellular automaton is equal to cpl init simple 2D, so 2 dimensions. And I can say I want to have size 60, 60, so 60 times 60, 60 rows, 60 columns. And then I can say, then I'm gonna copy paste this now because I don't want to do this manually. For those of you who know how the game of life works, there are certain structures that have names because they have certain behaviors. For example, you have a glider, a blinker, and so on. I'm gonna just copy them here because I prepared them for the video. And I don't want to type them out now manually. But you can pause the video and just copy paste them. So we have glider, blinker, and this is a lightweight spaceship. Basically just setting specific cells to 1. This is just an initial configuration. You can also start with a random state. It doesn't really matter. But these are interesting structures, which is why I'm going to add them here. And now, instead of just calling evolve, we need to call evolve 2D. But the rest is actually quite similar. We still have cellular automaton here. We still say that we want to have a couple of time steps. Let's go with 250 maybe. Then we also have to define a neighborhood. And the neighborhood, as I said before, it's going to be the more neighborhood. So just the 8 cells that are surrounding the cell that we're talking about. And then the apply rule is not going to be an NKS rule. It's going to be the game of life rule. So it's going to be CPL and then game of life rule. Yeah, basically just game of life rule because we don't need to pass parameters here. And we also want to say memoize equals recursive. So that still works. I think this should also work, but the animation is probably not going to work. So I actually wanted to comment this out. Let's see if this works. No, it doesn't work. Why is that? Because, of course, I think... Do I need to say plot 2D? I think I need to say plot 2D. What's the problem here? Next state is equal to... Oh, I shouldn't pass a lambda expression. I should just pass the game of life rule itself. And then I get the final result. Now, this is probably not what you want. You want to have an animation of what's happening. This is just the end result after 250 time steps. But we, of course, want to have an animation again. So what we're going to do is once again animate all of this. But this time, we're going to say axis set x limit is going to be 0 and 60, actually as a tuple. And then the same is going to be true for the y limit. And then I'm going to say image is going to be equal to ax image show. And I'm going to say cellular automaton 0. So the initial state, the interpolation is going to be set to nearest. And the color map is going to be just grace. And then what we do is we have an additional function called init. Let's say we have init here, which is going to just say image set data cellular automaton 0. I'm not even sure if that's not redundant. But let's just keep it like that. Return is going to be a tuple that contains the image, and then the animate function is just going to do image set data cellular automaton I. So this is now not going to be as before, because before we had a one-dimensional CA, and we didn't just visualize the one dimension with changes, but we actually visualized the changes along the second dimension. This time, we're not going to take the full game of life and expand it into 3 dimensions. We're going to just change the current image all the time. So we're going to just change this to I. And we're going to return as well just image, like this. And then we're going to say animation is equal to animation function animation. And we're going to say also here now init function is going to be equal to init. Animate is still passed here. And then frames are going to be 250, of course. Interval is going to be 50, or actually maybe let's do 30. And the rest stays the same. So let's run this, and you will be able to see that the game of life is running according to the game of life rules. So there you go. And that's it. Now, we can, of course, also start with a random initialization. I can say cellular automaton. I can comment all of this out here. And I can say that the cellular automaton is equal to CPL, and then init random 2D 6060, and then we would get a random start. Who knows what happens here now? It seems to... There you go. You can see that a lot of more stuff is happening since this is now random and we have a lot more stuff going on. But yeah, this is also how you can do that with the game of life rule. Another rule that we can apply, I'm not going to go into depth now on the explanation. Now, I'm going to explain game of life later on because we're going to implement it from scratch here. I want to show you how to implement custom rules. But we can also change this, for example, to the totalistic rule. So here we're going to say again lambda NCT, and we're going to say CPL totalistic rule. Actually, let's just copy paste all of this here that I have prepared, and let's remove all of this. Because what we can do then, if it's a simple rule, we can also just do plot2D animate, and then we're going to get a an animation here as well. There you go. So this is now an animation running on repeat of the totalistic rule with these parameters here. I don't want to explain now every single rule we use, but that is just one more example. The interesting thing now happens, in my opinion, when you define your own custom rules. So when I go ahead and I say, okay, for my simple 1D CA, I want to have my custom rule set. It shouldn't be an NKS rule. It shouldn't be a totalistic rule. I want to define exactly what happens here. This can be done easily by just extending from the base rule class. So you can say here custom rule, class custom rule here is going to inherit from CPL base rule. And then all we have to do is we have to override the call dunder method. So we have call, and what we take here as parameter is N, C, and T. So we get N, C, and T, and the most important one for us is just the neighborhood. So a very simple rule, for example, if we have a one-dimensional CA, is to just always, no matter what happens, for each cell, make it one state up. So in this case, we don't have just on or off. We have multiple states. So we can have state 1, 2, 3, 4, 5. We always just increase the state. This can be modeled by just returning here whatever n is, n1. Now, the important thing to understand here, I'm going to just implement this here, n1 is going to be increased by 1 here. The important thing is, in the case of a 1D CA, what you get as n is an array that looks like this. You have neighbor 1, then you have yourself, and then you have neighbor 2. So n1 is yourself, and not this n1. The n index 1 is yourself. N index 0 is your left neighbor, and n index 2 is your right neighbor, which means that in this case, I'm not even basing the next step or the next state on my neighbors. I'm just saying no matter what happens, increase by 1. Whereas I could do something like if n0 is equal to something, then do this or that. But in this case now, the rule is very simple. It's just always increase the state by 1. So we can say here the rule is equal to the custom rule. And then we can say cellular automaton is equal to CPL init simple. Let's do 100 and then we can say cellular automaton is equal to cpl evolve cellular automaton time steps equals 60, and then apply rule is equal to, now let me scroll down a bit, is equal to our rule. And then I can just say cpl plot cellular automaton. And then you can see this is the result of the CA. You can see that the middle is a bit darker because we start with 1 already. But I can also, I think, change this to just be an empty. I can also say MP array. And then I could just say 0, 0, 0, 0, 0, and so on. This would also work. And then we would not see a center line here. But yeah, we can also animate this again, just so we can see it in a better way. So what was it here? CPL and it's simple, 100. I can also go ahead and say figure and axis is equal to PLT subplots like this. And then mat is equal to axis mat show cellular automaton. Color map is going to be equal to binary PLT axis off, and then the animate function, again given an iteration, we'll just say mat set data cellular automaton up until I plus 1. And then animation is going to be equal to animation dot function animation figure animate frames is equal to 60, interval is equal to, what was it, 50, split equals to true, and repeat equals to false. Now when I run this, nothing happens because of course I need to also say PLT show here. What's the problem here? Did I mess up something? Oh, of course, I'm not returning anything. We need to return this as a result here. There you go. Now you can see how the animation works, how it gets darker. And of course, I can also change the rule here. So I can, for example, say I don't want to have just a simple rule. I want to base my decision. I want to base the new state on the neighborhood. So I can say return 1 if the neighbors are different. So the basic idea is if my left and right neighbor have not the same state, turn me on. Otherwise, turn me off, deactivate me. So you could say if n0 is not equal to n2, then you want to have 1 as your new state. Otherwise, I want to have 0. So yeah, this is just one rule that we could use here. That would be the result of that. And of course, this is also some NKS rule. In fact, it would be the rule where in this case you would get 1. So let me just think. It would be, you can actually see which rule this would be in NKS. This would be, in this case, 0. In this case, it would be 1. In this case, it would be 0. In this case, 1. Then 1, 0, 1, 0. That would be the rule. It would be rule 90. Yeah, it looks like a triforce basically here. Yeah. We can also go with something else. We can say I want to have darker if it's different. So I want to combine these two rules. I can say return whatever n1 already is plus 1 if the two neighbors are not the same. So if n0 is not equal to n2, and otherwise decrease the brightness by 1. So I can say do something like this. Yeah, but of course this is just an arbitrary rule. But that is the important thing that you need to understand. You can create your own rules by just looking at the neighbors. In the case of a 1D CA, that's quite simple. You have n0 and n2, the neighbors, and n1 is whatever you already have at this state. So you can base the next state on the neighbor states and on the current state as well. Now, let's move on finally to a 2D example. And for the 2D example, I'm just going to implement the game of life rule, but I'm going to do it manually. So I'm going to do the same thing here. But since now we have 2 dimensions, we're going to access more than just n1 or n0 or n2. We're going to go, for example, into n1, 1. So Game of Life has very basic rules. Game of Life basically says if the state of the current cell that we're looking at, so this would be n1, 1. Think about it that way. Maybe I can use here my paint again. Think about this, what we have here, and now assign the indices. This is 0, 0. This is 0, 1. This is 0, 2. This is 1, 0. This is 1, 1. This is 1, 2. This is 2, 0. This is 2, 1. And this is 2, 2. So these are my neighbors, and this is 1, 1 is the current cell. The basic rule now is the following. If the current cell that we're looking at is inactive, then if exactly 3 neighbors are active, this cell becomes active as well. This is just the Game of Life rule. If, and we can do that by saying the sum of n, the sum of the neighborhood, is equal to 3. Now we don't have to check for this one because it's already 0. So this automatically checks if exactly 3 neighbors are active. If that's the case, we want to activate the cell. Otherwise, we want to keep it inactive in all other cases if it's already inactive. Otherwise, if it's active, then what we want to do is we want to check if there is exactly 1 neighbor or if there's exactly 3 neighbors. In both cases, or actually, let me just see. The rule was that it has to have exactly 1 neighbor or exactly 2 neighbors. Yeah, that's the rule. So if the active cell has exactly 1 active neighbor or exactly 2 active neighbors, we keep it active. But if it has 0 active neighbors or 3 active neighbors or more active neighbors, it becomes inactive. So we say if NP sum of the neighborhood, now we need to do -1 because the cell itself is active and in the neighborhood. If that is equal to 2, so if we have exactly, or did I now mess it up again? Let me just think. In this case, we're saying that the sum, okay, sorry, it was 2 and 3. So if NP sum minus the one that is already active because it is itself, if that is equal to 2, or if that is equal to exactly 3, then we're going to keep this activated, otherwise return 0. That is now the rule set. But the rule set is not even that important. The important thing is that you can define your own rule set. You can write whatever you want here to define your own custom 2-dimensional CA. So this is now the Game of Life rule, but it's customly implemented customly. And now we can actually copy paste the same code from before. I'm gonna just do this here from my prepared code. Let me just copy this here. So I'm gonna remove that. I'm gonna say we want to have our simple structures here. And then I wanna do the evolution step down below. This is the exact same code that we had before. The only difference now is that we do apply rule equals rule and not Game of Life rule. So 250 here and 250 here for the frames. The rest is actually the same, so I can run this. And you can see we have, again, Game of Life, but we did it with our own implementation here. We didn't use the predefined implementation. And of course, I can change the rules of Game of Life if I want to. I can say, for example, or if the sum -1 is equal to 4, then you can also stay alive. This will, of course, mess up the whole CA, but it will be a CA that I can work with. Probably it's gonna be much more stuff is gonna happen, but it is a kind of CA that I'm creating. Actually, this is kind of interesting. It could be a nice maze creation. Yeah, it looks actually kind of interesting. But yeah, this is now my own CA that I defined here, my own 2-dimensional CA. All right, so this is how you can work with Cellular Automata in Python. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.